Alrighty, can you guys hear me again? Okay, so what I want to do here in the second half is look at some old exam problems. So let me pull them out on the screen. So you go in under modules in the Canvas account and you grab this practice 12 here. So a lot of these problems are related to fixed income, but some of them are related to foreign exchange. And the one I want to start with is this one, number 6. So it's a 2-period model. There are 3 time points, 0, 1, and 2. It's a foreign exchange model, so, and it's a binomial model as usual. We're looking at call options written on these forward exchange rates that we just talked about. So there's an option written on top of this foreign exchange forward rate. And we have to compute what the price of this option is, as well as the number of as well as the replicating portfolio, right? So this is what we're going to be doing, and then we'll do one more when we're done with this. So let me try to take you through what I had in mind with this problem. So we're looking at number 6. So this here is on the practice 12. So we're looking at a foreign exchange model that has there time 0, time 1, time 2. So we have a forward starting call. A forward starting call. So the forward starting, this means that the strike is set here at time 1, and the strike is F1. This is forward, or maybe we call it forward 1, 2. So this one here is F1 measurable. The strike is set at time 1, and the payoff, this is at time 2. Right, so here, this is when the strike is set. The strike is determined. And here, this is when we get the calls payoff. And the calls payoff, it's written on the exchange rate, it's written on Q2. It's a call, so it's Q2 minus the strike, and the strike is this quantity we have down here, the forward exchange rate. And so it's a call, so we need to take the positive part. Right, and what we're interested in is the initial price of this payoff. Any questions on what the problem is about? We want to figure out what is the initial price of a forward starting call. The forward starting component has to do with the strike not being a constant, but being a random variable that is set halfway through in this model, halfway through this model's time horizon. So time one, the payoff of the call comes at the end. It's a call written on the foreign, it's written on the exchange rate. And we want to know what the payoff is worth at time zero. Any questions on the setup? So the first thing we could do is to figure out, so we always need martingale properties. And so the martingale properties we need is we have our SN, right? Remember SN, this was the risky security. So this is the foreign bank account. This is the foreign bank account converted into US dollars. So if you write out what this is, we will get 1 plus RF to the power N times QN. And the martingale property we have is, so under the P tilde measure, Sn divided by the domestic bank account, right? So this is equal to Sn divided by 1 plus R to the nth here. This is a martingale. So let's just write out what that implies. Well, we will, for example, have that if I compute the conditional expectation of this thing here at a later time point, so say n plus 1, so n plus 1 would be 1 plus Rf n plus 1 times Q n plus 1 divided by what we have downstairs, 1 plus R n plus 1. I would get that this is exactly the same as the current value. So this would be 1 plus Rf n Qn divided by 1 plus R to the nth. So what this allows me to get a grip of is how the Qs do work over time. I can simplify this. What can I do? I can simplify this to say that the conditional expectation of Qn plus 1, what is that going to be? The conditional expectation of Qn plus 1 is going to be 1 plus R divided by 1 plus Rf times Qn. So this is not a martingale property of the Q, but it tells me how the conditional expectation of the exchange rate, how the conditional expectation evolves over time. Okay, so the first order of business is going to be to figure out what the forward, what that strike is going to be. So let's figure out what this thing here is. So that was what we did before, but let's try to redo some of it maybe. So we will see that, so for the forward price, the forward foreign exchange rate if OR12, we know that it solves. We know that it solves this Q2 minus, and then like this is F2 measurable. This one here is F1 measurable. This is the payoff of the forward. This is the payoff of the forward at time 2. Right, so the value of this thing, so the value of this payoff at time 1, we'll have to discount it. So we'll have to discount it back 1 period. So this is conditional expectation up to time 1 over 1 plus R, and then Q2 minus, right? And then the forward exchange rate is made such that this value here, the value of getting this payoff, this should be 0. And then we just solve, we're going to get exactly the same formula as we had before. The forward exchange rate is simply just a conditional expectation of the exchange rate. And we figured out what that was. We had the formula right up here. This was equal to 1 plus R divided by 1 plus RF times Q1. And sanity check, right? This here really is F1 measurable. Which is what it had to be. Are we good so far? Are we good so far? Dawn is okay. So then, so we know at least what to put in here, right? And then we move forward, try to figure out, okay, so what is the calls payoff? Well, now we can plug in what we just figured out. We now get that the calls. So the calls payoff at time 2, this was Q2 minus this forward exchange rate positive part, and then we can plug in what this is. So this is going to be my Q2 minus, and then that formula we had right here, 1 plus R divided by 1 plus RF, and then Q1, the positive part. Okay, so now this is the payoff that we then have to roll back to time 0. So maybe we should draw the tree. There are some specific numbers here. So to get values, to get numerical values, we're going to use, what were the values? It starts out at 4, and it goes up with 3 over 2, and it goes down with 1/2. So let's grow the tree. So it goes up to 4. It goes from 4 up to 4 times 4 times 3. Just make sure I didn't mess up my values here. I did it right. Okay, so 4 times 3 divided by 2. So this would be 12 divided by 2. This is 6. And then it goes up to 6 times 3, 18. So let's go up to 9. Go down to a half. And then it would go up by up to 3, and then go down to 1. So this is my Q's. So this is Q0, Q1, Q2. We need to have something about the R's as well. There were some values given in the problem. They were also given a value for R would be 25%, and RF would be 50%. So, so we should look at the ratio 1 plus R divided by 1 plus RF. This would be 1.25 divided by 1.5. So we will be interested in this payoff here. This will be, maybe we should write that in red. So it will be 9 minus 9 minus, should pick some better numbers here, 1.5 times the value of Q1 on this branch. This will be 6, positive part. Just want to make sure I got the right numbers here. So what do we get here? This is 1.25 divided by 1.5 times 6. Yeah, I think I messed up in my solution. I wrote a 3 in the solution. This is off. Let's make sure I got it right. So 1. Yeah, I get that this here is equal to 4. W2 is going to be 3 minus so there'll be 2 values now because it depends on whether you go up or you go down. So that'll be, just split this into 2. It'll be 3 minus 1.25 divided by 1.5 times 6. So that's going to be 0. And then the other one is going to be 3 minus 1.25 divided by 1.5 times 2. And that's going to be get here 1/3. Double check that. And then the last one will be the exchange rate is 1 minus that ratio, 1.25, 1.5 times 2. I think that's going to be a 0. Yep, that's going to be a 0. Right, so the thing to note here is right, there's a difference between 6 and 2 here, because you need to know what the exchange rate was. On the lower branch it would have been 2, so that's that 2, and then on the upper one is that 6. Are there any questions on what we did here? So now I have the payoff.
Y.
Yep. Go ahead.
YQ1 should be divided by 1 add RF.
Can you say that one more time?
YQ1 should be divided by 1 add RF.
You're talking about this formula here?
Yes.
Well, so what is this?
Forward 1, 2.
So if you go on the previous slide, right, we worked it out to be 1 plus R divided by 1 plus RF.
Well, I know, and I know 1 plus R, but I don't know 1 plus RF.
So it's this. It's so your question is, why is this one here true? Is that correct?
Yes.
Okay. So you agree on the first one. So the question is, why is the conditional expectation of Q2 given F1 equal to this expression here? And so what you do is you go up here. In the beginning we had, so this is on number 16. So in the beginning we had, what are the martingales we have in the problem? Well, you discount risky securities by the bank, and then you get a martingale, right? So Sn divided by the bank, the martingale. So from this equation here, you move the bottom one to the other side, and you move the top one to the other side. So from this equation, you're going to get this one here.
Okay, thank you.
Right, and here this is RF downstairs.
Okay.
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 Other questions? So now we have the payoff, and we can now roll it back. We need to use the risk neutral probabilities. We need to figure out what those are. Those risk neutral probabilities are. So we've done that a number of times, but we can do that again. If I have a binomial model, so this here will be following up on Ms. Wang's comment. Like if I have a binomial model for this one, I can write this here as the conditional expectation under the risk neutral measure of Qn. Right, so that's the relationship between Qn and Qn plus 1. This is given by these coin flips. And Qn is going to be Fn measurable. So from this expression here, we will actually get what the risk neutral probabilities are, as we did on an earlier slide as well. This will be, it's not working. And this here will be, well, let's take it in 2 steps. This will be Qn, and then P tilde, and then we call it UQ, plus 1 minus P tilde times DQ, that's equal to this 1 plus R divided by 1 plus RF times Qn. And so we can say then that this is the same as P tilde UQ plus 1 minus P tilde times DQ. That is exactly the same as 1 plus R divided by 1 plus RF. And now we solve for P tilde. So P tilde is equal to, can we do this in one go? We will move DQ to the other side. So 1 plus RF divided by 1 plus RF minus DQ. And so what we have left is UQ minus DQ. Right, that's my P tilde. And so we'll need those. If you want to do actual numbers, we need to figure out what are those values. What is P tilde here? So we had, this was one ratio, so we had P tilde is equal to that ratio, 1.25 divided by 1.5 minus DQ, that was a half, divided by UQ, that was 3/2, minus a half. So what do we get here? Bottom one is 1, top one is 1.25 minus 1.5. Something is way off with these numbers here. Minus, again, a third. Let's double check this. Third. And so now, given I have the risk neutral probabilities, we can move these ones forward as we've done so many times before. So for example, if I want to know what the value is up here in the top node, so if I want to know what V2, so I'll roll it back. So V1 in the up node will be, I discount the payoff. So this is 1 over, and these are now all in the domestic currency. So this is 1.25 times, and then the risk neutral probabilities is a third times 9, not times 9, times 4. So the other one is a 0. And what do we get down here? This will be the V1 of D. This will be these two payoffs roll back. So we're here in the upstate. This is 1 divided by 1.25, 1 over 3 times 1/3. This will give me the two values here. And then, of course, if I want, I can also get V0. V0, I have to roll these two payoffs back to times 0 will be 1 over 1.25 times the up probability, that was a third, times this payoff, that was in the upstate, plus, and then the probability of being in a downstate, 2/3, times the payoff in the downstate is this guy, 1 over 1.25, 1 over 3 times 1/3. So whatever this number is, this is going to be the value of the call. Are there any questions on this? Let's try to do another one. The other one is it's not that different. The other one is problem number 9. We'll bring up question number 9. So this was number 6. So this is number 9. So it's again a 2-period model. There are these forward exchange rates, and he's being asked that the foreign exchange rates are using a binomial model. Okay, we consider European call on the exchange rate. So we're looking at the underlying now is this forward, and again we're being asked to compute what is the so if here's the forward rate, we're being asked to compute what is the price of the call option and what's the replicating portfolio in this specific example. So let's try to work this out. So again, it's a 2-period model. We're looking at so now the model is we model Fn using a binomial model. So in this case, it's Fn is equal to the previous one times the size. The size have this usual form. It can go up, it can go down. It can go up to 2, it can go down to a half the IID. And these ones here, these are the forward. These are the forward exchange rates. So these would be what we had denoted before by FOR. And this is a 2-period model, so this is N2. So this is what we used before. In this particular problem, they just called F. So if I write out what the forward exchange rates in this binomial model, how do they look like? They are given to start out at 4, and then you can go up and down. So instead of Q being the underlying, now it's the forward exchange rates that are the underlying. So you can go down you can go up and down with these factors. U is 2, so it's 8. U is 2, and then D is a half, so it's down to 2, and then up to 16. To 16, then 4, 4, and 1. So this is F0, this is F1, this is F2. And so what we're interested in is the payoff of the call. This was F2 minus, what was the strike? It was 4. So we will have here the payoff of the call would be 16 minus 4, positive part, that would be 12. You get 0, 0, 0. And so then the name of the game is to move this thing forward. You're also being told that the interest rate is 25%. So what remains is to figure out what the risk neutral probabilities are. Right, because as soon as we have the risk neutral probabilities, we will just roll these ones. We discount, we roll them forward as before. We figure out what the risk neutral probabilities are. Well, we know. So again, we go back to the material that we have been through. We know that the forward rates, there's a martingale structure in there. Like we know so we need to find, so to get the risk neutral probabilities, we use, what do? We use that the forward, we had this NM, but this will be equal to an expectation of QM. This was true for n equals 0, 1, all the way up to m. Which means that this is a martingale. Right? Remember the argument for why this is a martingale, because of iterated expectation. So if you look at the forward at time n plus 1, you plug in the definition. At time n plus 1 of QM. And then you use iterated expectations and get that this is nothing else than the conditional expectation of QM given Fn, and this is my forward rate at time n. Right, so we use that to have a martingale. So we usually have a martingale, and we have this structure here. Okay, so because, okay, so this is what we've done before. So because this Fn is a martingale, we'll have that the conditional expectation of Fn plus 1 is equal to Fn. So now we're back into the problem. This is what we did in class before the break. We plug in this this formula, we'll get that this is E tilde n Fn, and then the coin flip. This one here is measurable, and this one here is independent. And so we get Fn times P tilde, and then the coin flips, this was U and D. Right, so we solve, we have Fn here, they will cancel out. We're gonna get that 1 minus D is equal to P tilde times U minus D. So we're going to get here that P tilde is equal to 1 minus D divided by U minus D. And then we can plug in what the various values were. We had them up here in the beginning. U was 2, D was a half. So we're going to get a half divided by 1.5. U was 2, D was a half. So we're going to get 1 minus a half. That's a half. U was 2, 2 minus a half is a 1.5. And see what we get here. Third again. So now we have the probabilities. We have the payoff. We're just going to roll it back. So now we have the payoff, we have the risk neutral probabilities. We can now roll back, roll to time 0, the payoff, which was 12, 0, 0, 0, right? So we're going to roll these zeros, will of course be 0 here. This 12 will be what? So there's a third probability, there's the third risk neutral probability of going up. There's a 0, 2/3 of going down. So we will have here will be 1 over the domestic rate was 1.25 times a third times 12. So this is the price of that payoff for that time 1. We roll it all the way up to time 0. 0 is still down here, so we're going to get 1 over 1.25 times a third times whatever we have here, 1 over 1.25 times 1 over 3 times 12. Okay, so this here, this is the call price. Are there any questions on how we computed that initial call price? There was one more question in the problem, so let me just bring it up again. This was like compute the arbitrage-free price in domestic currencies or in dollars, but it also asks about how should we trade to create this replicating portfolio. And this is a little bit trickier, so maybe I should try to spell this one out here in class. So let's see if we can figure out how to trade. Page 22. So how to trade to replicate the call. Right, so we can trade in two things. We can trade in the bank. So this is the dollar, the domestic one. And then we can trade. It's given here that you can trade in forwards. You can trade in forwards. So these are the two things you're given that you can trade in. So let's just recall how to set up this replicating portfolio. So we can trade in the bank, we can trade in the forwards. So these are forwards. This is on the future exchange rate. It was F2, which was my Q2. Let's try to figure out how should we trade in these objects in order to replicate the call. So let's just recall the wealth dynamics. The wealth dynamics. So we have, so the wealth would be, well, the definition would be the number of units. So the number of units times the bank plus, and then the number of units times the risk of security. Whatever, so this here is the, this is the risk of security. So we use a self-financing condition, which we've had before. This is the self-financing condition. It says that whether I put n plus 1 at the prices or not, I'm going to get the same value. So here I can write Sn0. That's not right. The value of my portfolio before a change is the same as the value after a change. So whether I write n plus 1 here on the holdings or I write n, I get the same value. So I have this. And then I can use that this quantity here, this is equal to, this is the domestic bank, so this is 1 plus r. And I get this familiar formula that says 1 plus r times, and then it's xn minus, and then the stock position, delta n Sn plus delta n Sn plus 1. And I'll get 1 plus r times x And then I'll have my delta n Sn plus 1 minus 1 plus R Sn. Okay, that's the long story short. That's a long story short. So what we're going to be applying this to is the case where we can trade in forwards. We trade in forwards on this future exchange rate. So this is going to be my Sn. And here in particular, we're interested in the initial position. This is my delta 0. So what should we write here? So we recall again that so when the risky security is the forward, when the is the forward. What do we have? We'll have so we will have on one hand the value of Qn minus Fn. Right? If I enter a forward at time n, what does it cost to enter a forward at time n? Well, I have to discount this thing back to time little n, so I discount it back to time 0 and then move it forward to time little n, and I want to compute the conditional expectation. So this is going to be equal to 0. That's how we get Fn. So this is what we've seen before, right? This gives me that Fn is equal to the conditional expectation of the future exchange rate. Right, so over here, this is my Sn. So the cost of entering a forward at time n for the fair forward rate, well, that's going to be 0. So that's one of the quantities that go in here. The other one is more tricky because how do I get the other one? So now I've entered this contract, and I need to figure out what the value is. So if I'm looking at E tilde n 1 over Sn0, so here I have n, but now instead of n here, I'll have Sn plus 1. This value here is going to be my Sn plus 1. I've entered one contract. The contract pays out this quantity here at time capital N. I'm sitting at time n plus 1. What's the value? This here is going to be my my Sn plus 1 in the formula up here. And we can work out what it is. We have the ratio between the two bank accounts. So we'll have upstairs it'll be 1 plus r to the power n plus 1. Downstairs it'll be 1 plus r to the nth. And then I'll have the conditional expectation of Qn minus Fn. And this we already know what is. This is this quantity here, this is my forward at time n plus 1. So long story short, in this setting here, my wealth at time n plus 1, it is this mass I have, 1 plus r xn blah, 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 blah. Let's plug it in. So my wealth at time n plus 1, this is going to be that mass we have over here, 1 plus r xn plus, and then delta n times Sn plus 1, what I have here. This is 1 plus r to the n plus 1 divided by 1 plus r to the nth, and then times the increment in the forward prices, Fn plus 1 minus Fn. Then we have minus this 1 plus rs, but it was a 0. So that's my wealth. When I can trade in forwards as the underlying. So let's try to figure out what the replicating portfolio is. Let's figure out what the replicating portfolio is. Branches, we figured out what the wealth is at time. We figured out what the value is of the call is at time 2, what the value of the call is at time 1, what the value of the call is at time 0. So now I want to figure out what is the replicating portfolio at time 0. What is my delta 0? Like this was the starting point, right? We wanted to figure out what is delta 0. So let's try to do that. Like I want so to get delta 0 or delta n more generally, we want the value of the wealth. So this is my xn plus 1. What kind of a wealth do we want? Well, we want a wealth that has this value here, the red one in the up state, and this one here in the down state. So we want this quantity in the up state. We want this quantity 0 in the down state. So we want this thing here to be what is this function? What did it call it? Bn plus 1 that we condition on. So maybe we should just do delta 0. So let's maybe just do delta 0. So, right, I want my wealth at time 1. I want my wealth at time 1 to have these two values. So we want to have it to be in the up state. I want 1 over 1.25 times 1 over 3 times 12. In the down state, I want a 0. And then we write out what the replicating equations are. There are going to be two equations. This is going to be 1.25 times 1 over 3 times 12. This is going to be something, and then 0. This is going to be something else. Plug in what x1 is. Plug in what x1 is. Plug in what x1 is. That's the formula. So x1 is 1 plus r times x0 plus delta 0 times 1 plus r divided by 1 plus r. N here was 2, so this is a squared. Then you get f2. So f2 here is F1 times U minus, so this is if n is equal to 0, so this is F1, so this is F0 times U minus F0. N is equal to 1, no, n is equal to, I keep saying 1, n is equal to 0. So 0 here, 0 there, 0, and then it'll be 1. So let's say 1 in the up state, and then, yep, that's good. So and then get 1 plus r, x0 plus delta 0, 1 plus r divided by 1 plus r squared. And then instead of a u here, you need to put a d, and then you get this. And so we go ahead and you solve, and you're going to get, so you can solve for x0 and delta 0. And whatever you get out, this is going to give you what that replicating portfolio is. Any questions on this part? So what made this more complicated and what? Yeah, go ahead. Go ahead.
Oh, this is just like a dumb question, but like, since it's saying that we're only moving like in a forward direction, then like the heads, the path towards the heads is the only one that's positive, while the others are negative, right?
Don, can you say that again? You're echoing.
Oh, okay. So what I meant to say is that like, since for the risky security is like moving forwards, then like the path from 4, 8, 16 is the only one that has a definitive value, while the other paths are just 0, right?
Yeah, so we did, don't make no mistake about it, we did go backwards here. We did go backwards.
Yeah.
Because
Right.
to get this value here, we went backwards. So this value here is something you found from going backwards, and that's a key component in the last slide, because in the last slide, that's the left-hand side.
Okay.
Right. This one here comes from backward.
So
you do all the
yeah, that was a
questions,
question, sorry.
and then you go forward.
Okay.
Which is exactly what, I mean, we have been doing that for the standard European options too. Right? We will compute all the prices, and we will compute, like for the like for equity, we would have like Fn of Sn. That would be our starting point, and then we would form Fn minus 1 of Sn minus 1, and the way we would do that would be to compute the conditional expectation of 1 over 1 plus Rn Fn Sn, right? And so we would compute all these all the way down to F0 of S0. So then we would move forward. So that gave us this Fn of S0. So now given that, we would start moving forward in a tree. And so how would we do that? Well, we'll say, so set x0 to be f0 of s0, and then solve x1 being f1 of s1. And this is where you get two equations. So this is going to be this would be the same thing as you have. Let me write it out. This would be delta 0 times S1 plus delta 0, 0, S 1, 0 should be F1 of S1. And then over here, we will write that as S 0, 0 times 1 plus R. And then you would write that entire thing here as x0 minus delta 0 S0. So you end up with an equation that is exactly what we had before, except for equity. You have this would be you have S1 minus 1 plus R delta 0 S0. There's no delta 0 now. You have this plus x0 times 1 plus R. You need that to be equal to this F1 of S1. Do you agree?
Yeah.
And so now you solve for the two unknowns will be your delta 0, and x0. You have two equations and two unknowns because the two possible values of S1. S1 can be S0 times U, and S1 can be S0 times D. So you get these two equations and two unknowns, you solve for them, and then you hope for a miracle because your x0 that comes out of this exercise better be the one that you had up here. But it is.
Okay.
So what we did in this last exercise here is this is exactly what we did here, except the underlying was not a stock. What we're doing over here is we again have our two equations. The two equations, this thing here breaks out into two equations. This here breaks out into delta naught, and then it'll be S0 times U plus 1 minus R S0 plus x0 times 1 plus R being F1 of S0U. It breaks out into delta 0 S0D 1 minus 1. Is it plus? It is a minus plus x 1 plus R. This is F1 of S0 times D. Right, this equation here, this breaks into these two. And just as this one over here, you want your x1 to be equal to whatever we had on the right hand side, so it breaks into these two equations. And so you can see they're quite similar. You have your x0 times 1 plus R in both of them. X0 times 1 plus R, x0 times 1, this is the same. What differs is what you have over here with the delta 0. This differs because you don't have equity. Like equity says that the stock price at time 1 is equal to the previous stock price times the outcome of the coin flip. So U and D. That's not the case when the underlying is forwards. And so that's why this term here, it looks quite similar, but it's not exactly the same as what you have here. It's a bit different. And I mean, it's not that different, but it is a bit different. Like this term here is not quite the same as this term you have here. And the reason that they differ is because the underlying is not a stock. The underlying is this forward, but when you enter a forward contract at time 0, that's free. This is what is meant by the issue, right? So when you enter a new forward contract at time n, so if you take n to be 0, then the cost of entering a forward contract is 0. So when you subtract away, so S0 in this example here, like the stock price is typically not 0 in an equity model, but if you have the underlying being a forward, then the initial forward, the cost of entering this forward contract would be 0, so there would be no S0s here. So that's why we had to go through this exercise about how to write the wealth dynamics, but for the case when the underlying is a forward. Right? So then we need to know what is the thing that we're interested in is like, how is x1? X1 is going to be equal to 1 plus R x0 plus delta 0 times this ratio. So n here is 2. So we're interested in type 1. So this is f1 minus f0. That bottom formula, this is the one that we're interested in. And so it's this x1 here that has to be matched up with what we had in the tree. And the tree was what we had here. And we computed these two values in the tree by going backwards. So it's quite similar. Can you follow?
Sorry, it seemed like a dumb question, but yeah, I get it.
Yeah, so it's similar to what we've been doing. The main difference is that the underlying is not a stock. The underlying, for whatever reason, the underlying is given in the problem to be something else. It says where at any time n we can trade a forward on the exchange rate. And so it's given that you can trade in the bank because there's a bank rate, and then you can trade in these forwards.
Mm-hmm.
So then the question is, how does your wealth process look like when you trade in forwards? And you see, entering a forward contract is free. Whereas when you did equity, buying a stock is not free.
Mm-hmm.
So the wealth dynamics are going to be a little bit different. And this is what we're seeing. But the mechanism that we're doing is the same. You go backwards in the tree, and now we have all these conditional expectations, and then you go forward. So that's the same.
Okay.
Are there other questions or comments? So we are here. Next time is going to be the last lecture. And I'm not sure what you guys would like to have happen in the last lecture. If you want to have, I don't know what you guys would like to have happen in the last lecture. So do you want to see more material? Do you want to see, problem solved? Do you want to see these exam problems solved? What would you?
I mean, I'd like to see like more examples of problems.
So like what we've been doing here in, did you say exam problems or did you say just problems in general?
Problems in general. That also includes exam problems.
So there was a question out here in the chat. Ms. Wang says exam problems. Okay. So the alternative, so let me just put up what the alternative is. The alternative is to do this chapter on Black-Scholes. Show you guys how you can take these discrete models that we've been working with, passing to a limit, and obtain the Black-Scholes formula. So far I have 2 wishes for looking at problems, like what we did some today, and we can do more of them next time. Are there any other students that want to say something? Shumik is saying exam problems too. So Dawn, is that okay with you, or do you want, because an alternative is all these Wednesday sessions where there are other problems being discussed. So
that's fine.
If there are specific problems from these Wednesday sessions that you would like to have me discuss, if any of you have any problems that you would like to see me solve, not the exam problems. I'll pick some of them up and we can go through them on Tuesday. But if there are other problems that you want me to solve or discuss, if you can let me know sometime over the weekend, which problem. So Dawn, if you have something specific, if you can let me know sometime over the weekend, then I have a little chance of looking at them before the lecture.
Okay.
We can go through that on Tuesday. Otherwise,
All
I'll
right.
start with these
I
examples.
think if any like specific examples, I'll let you know.
Yep. So there's this practice set number 12. The idea is to have Xiao go through the, we only did 2 of them. I think there are like a handful of problems with foreign exchange. So the goal is to have Xiao go through them next week. Okay, I think this is a place to call it quits unless there are questions. So just for Thursday morning, the office hours, you will start at 8. On Friday, it's the same. Next week, it's the same. Okay. Any other questions or comments?
I think it's just a comment, but I've noticed that like the problem 9 is kind of like similar to like problem 2 in the homework 10, albeit a little different.
Yeah.
And I really I noticed that like in problem 2, there's no given F0. So
No,
is there like a different way to approach that?
You have to work out what this F0 is. But there's a formula for it, right? So
so we have to find F0.
yeah, you have to find F0. But
Right.
we already have it. We already have it.
Oh right. Okay, never mind.
Just, bring it back up here so we can see.
Okay, never mind.
We already have F0 because we have this formula here.
Yeah.
So if I want to get are you talking about question? You're talking about problem 9.
Problem 2 in homework 10.
Problem 2.
Yeah, but I noticed that like you can just find F0 by using R0, so never mind, I guess.
Problem 2, is that on the homework or is that somewhere else?
Yeah, the homework.
Okay.
But like I just noticed that they're like similar to problem 9 here, albeit a little different.
Let me just bring it up. Is this homework 9 or homework 10?
Homework 10.
Yeah, so here in this question, you can you'll use that that there is a way to compute these forward rates.
Yeah.
By conditioning. So you can work out what these FNs are in terms of these epsilons distribution.
Okay.
There's this conditional expectation that we've had before, right? So the forward rate, you go one back by conditioning, right? And so you know how to do that. So you go backwards like this, and you're ultimately gonna get what F0 is.
Okay, yeah, I see it.
Okay.
The thing I was confused about is how to like find F0 by using this, but I guess I could just do that by just like Fn is equal to 1 minus Rn. So
Let me just show you.
no, it's okay.
No, I mean we have time to do this.
All right.
So the we have an n-period model. So if you look at the forward at time n-1,
Yeah.
how would this be set? Well, this is going to be Fn measurable,
Right.
and you're going to have that the payoff at the end. So you're looking at forwards or futures. Is this a futures or a forward contract? This is a futures.
Yeah.
So Fn-1, this is going to be the conditional expectation of the terminal value, which is the whatever is given. This is 1 minus Rn, right?
Yeah. Yeah.
And so, and then Fn-2 is going to be the conditional expectation of
1 minus R and minus 1. Yeah.
no, there's no -1 here.
Oh, okay.
Right, so this is going to be the same thing as the conditional expectation of this guy.
Oh, okay.
Right, by iterated expectations.
Mhm.
And so you can then you're going to keep going. If you want to give F0, this is just going to be the expectation of 1 minus Rn.
Okay.
So if you were to, for example, compute what this one here is, you can you will get this is 1 minus, and then you use the formula. You use the formula for this thing here. This is
Yeah.
E tilde n-1 of Rn.
Right.
This thing here is Rn-1 times epsilon n,
Hmm.
and Rn-1 is measurable, so you can travel outside. So this here becomes 1 minus Rn-1, and then the expectation P tilde, is it U and D again? Probably U and D. Plus 1 minus P tilde times D.
Yeah, and then that would be like 1 minus PU, like RN plus 1 times PQ plus QD. So.
Yeah.
Okay. Yeah. Okay. Yes. Now I see it.
So that gives you Fn-1. So if you're going to get Fn-2, then you have to compute the conditional expectation of this quantity here, but given Fn-,
Okay.
and then you
All
keep
right.
that until you get to F0.
All right. Okay. Got it. Thank you.
Okay. Other questions or comments?
Hello, I want to ask. Hello, Professor. I want to ask that what is Borel subsets?
Oh, yeah.
What is Borel subset?
So if you take so B, this is a sigma algebra. This is the smallest sigma algebra, such that say sets like this, such that sets like this belong to B for any x in R.
Another question. Another question. Let me open my camera. Where's my camera? Okay. How to get this from this?
Can you point again?
How to get this from this?
Well, the first term is the covariance, right?
Mm.
And then the second term, the minus, this is going to be minus rho sigma 2 over sigma 1 times the variance of x. Right, so that's probably sigma squared.
But how to get it? How to get it? I just want to know.
I'm not sure I understand. If you're looking at can you see my screen?
Yes, I can see your screen.
So E of EX minus X squared, right? This here is the variance of X.
Yes.
And this is probably your sigma squared. I mean, this is the definition, right? This is the variance by definition of a random.
Wait, let me write it. Let me mute for a moment.
Okay. Are there any other questions? Well.